Okay, our conical pendulum. So there is a visual representation of it. As I say, the bob, or the helicopter, is flying in circular motion, horizontally, attached to our string up at some point at the top. So the important features we need to know. I was trying to move it with constant angular velocity, and so there's omega. It created our cone with a radius r, height h, and then theta is just the angle the string is making with the vertical. Now, just like all the others, the first thing I want to do is draw up a force diagram. So there's good old Bob. All the forces that are acting on this particle at any instant. Okay. It's attached to a string. So like I mentioned the other day, anytime it's attached to a string, you will get tension, and tension will act away from the object. So it's going off whatever angle the string is making in that direction. And we also have our force due to gravity. That's it. They're the only forces acting on this. So yes, it is moving in circular motion, but remember that was a resultant force. It's not actually a force acting on the particle itself. Now, like with projectile motion, where we resolved it into horizontal and vertical components because it's easier to work with straight line motion, we're going to do the same thing here. So our tension will need to be broken up into a horizontal and a vertical component. So that's why the angle the string makes is important. So let's just draw this up. The resultant force horizontally, mx double dot. But as I said, horizontally, it's just moving in a circle. And we said the resultant force of circular motion is the centripetal force. So I know horizontally, the resultant force is mv squared on r. Vertically, if I am doing it constant, then it should be staying on that level plane. So vertically, it's not moving up, it's not moving down. That only happened, remember, when we sped it up. When we sped it up, it did then rise. But if I'm keeping it at a constant velocity, it's not moving up or down, so the resultant force is zero, because nothing's happening vertically. So the way I like to set this up then is I think in my head, okay, well I know all the horizontal forces, or in the x direction, is going to equal mv squared on r. And I know all the vertical forces will sum to give zero. And so I now draw two separate force diagrams, one for horizontal, one for vertical. But as I say, I need to break up my components. So I'll have a horizontal component of tension and a vertical. And I've drawn the arrows, so I need to go to the left. So horizontally I'll be going to the left, and then up to get to the same point. And that's, as I say, is why the angle the string makes becomes important, because we can use a bit of trig now to work out the horizontal and the vertical component. So all right, let's have a look horizontally. So that component would become t times sine theta. But that's all we've got, because gravity is purely vertical. So the resultant force must equal t sine theta. And remember, the resultant force for circular motion is always going towards the centre. And so look at the direction of our horizontal force. Yep, that is going towards the centre. It's in the same direction, so it is positive. So t sine theta is mv squared on r. Or if I was using angular velocity, it would be mr omega squared. Over vertically, so I now have a vertical component of tension going up, t cos theta, but I also have gravity going down, mg. They will sum to give zero, because the resultant force vertically was zero. And so I can rearrange that and get t cos theta as mg. So I now have a couple of equations I can play around with and find different things. One of the common things we do is combine the two, and I get, that way I don't actually need to know what the tensions are, because that will divide out. And I end up with this equation, tan theta is v squared on rg. So depending on what information I have, I can find, I might be able to find the velocity if I know the angle and the radius, or I might be able to find the angle if I know the velocity. If I was using angular velocity, that would turn out to be r omega squared on g. Now, interesting thing is, I could also look at that triangle and come up with another expression for tan theta. It would be the radius over the height of that cone. And so subbing that in, I get v squared over rg as radius over height. Rearranging that, I've now got an expression that could work out how far that helicopter or that bob is below my spinning point. So it would work out to be r squared g on v squared. Or simply g on omega squared if I was talking about angular velocity. But that makes it interesting. If I look at it as g on omega squared, g, remember, is constant. So we're saying, really, the only thing controlling how high the helicopter or the bob goes is the angular velocity. Again, that is why when we increase the velocity, because velocity is on the bottom of the fraction, increase the velocity, then we decrease the height. So it rose because the cone's height became smaller. So the depth of the pendulum, is the technical word for it, is actually independent of the length of the string. That didn't matter. Well, to a certain point, because obviously it couldn't be lower than the length of the string because the string can't grow. And as I say, as the speed increased, our particle rose. So here's an interesting question that we could solve. If I was going to increase from 60 revolutions per minute to 90 revolutions per minute, how far would it rise? So if that was the question, I would set it up just like I did that last one. The first thing I do is I draw my force diagram. I say, okay, I've got tension and I've got gravity. But I'm going to need components. I also know that's r over h and theta. I know all my horizontal ones will sum to give mv squared on r. All my vertical ones will sum together to give a 0. And so just like I did before, let's draw the horizontal ones. Again, it's t sine theta. This time I'm using angular velocity because in the question I'm talking about revolutions per minute. So mr omega squared. And vertically, there we go. So we're interested in finding how far the height rises. So tan theta, I'll use that expression. I get the r omega squared on g, but using the actual triangle, we know tan theta is also radius over height. So I come up with my expression h equals g on omega squared. It's now really just a substitution question. So initially it was 60 revolutions per minute, but I want radians per second. So that turns out to be 2 pi radians per second. The height at that point, well, the exact value for the height is g on 4 pi squared. Okay, well, when it's 90 revolutions per minute, and that turns out to be 3 pi radians per second, we get g on 9 pi squared. So the rise, of course, must be the difference between the two. So approximately 0.14 of a metre or 14 centimetres it would have risen. Here's an interesting one that was in the HSC in a palindromic year of 2002. So we've got our mass of just m, length of the string is L. We've got a fixed point up the top here, but it's actually sitting on a cone itself. So not only is it moving in a conical pendulum, it also rests on a cone. Constant angular velocity omega. We're told that our cone that it's sitting on, the angle at the top is 2 alpha, and alpha is bigger than pi and 4. String also makes an angle of alpha at the top here, and they've told us all the different forces. So we have a string, tension's up the string. Now it's time to introduce a new force. Talked about this when we were talking about Newton's third law and how I could just stand here and not fall through the ground, and the reason being is there actually is a force of the ground is exerting on me as well. Anytime you're in contact with a surface, there is what's called a normal or a reaction force going away from the surface. And so that's this one in the diagram here represented by N. So it will be perpendicular to the surface. So that N is at right angles to the surface of a cone. Okay? And we'll talk more about that when we look at bank curves in the next section. And we've got the gravitational force as well. So that's what I was just saying. So anytime particle makes contact with a surface, we're going to have a normal force which is perpendicular to the surface that it's sitting on. So show with the aid of a diagram. So that's your force diagram basically, because they like you to draw your force diagrams. It's the most sensible way to approach the problem. you need to know what forces you've got. That the vertical component of the normal force is n sine alpha. So, okay, there's Bob. We had tension going up the string. And so we've got components of that. And using alternate angles, if you have a look at that original diagram, alpha was the angle it made with the horizontal at the top. But alternate angles means alpha would be the one down the bottom here. And then we had the normal force. Got to be careful here because it wasn't perpendicular to the string, but it was perpendicular to the surface of the cone. Now, let's just redraw it over here so I can work out where alpha is in our diagram. Remember the cone that it sat on had an angle at the top of 2 alpha. So I've just split it in half here and said that one would be alpha. So we can now use some geometry. Again, I've got some alternate angles. Alpha would be there. We know that that normal force is at right angles to the cone. So therefore the one down there is 90 minus alpha, so the one up here must be alpha. So in our triangle, alpha must be at the top here. So that now allows me to find the vertical component of the normal force. We've got gravity, of course, coming down as well. So let's call the vertical component C. That's what I'm trying to find. And because it's a show that, I can't really just quote it because they've given me the answer. I need to set it up very simply by saying, oh, well, C over N would be sine alpha. So C is N sine alpha. So yes, the vertical component is N sine alpha. All right, they now want us to show that T plus N is this wonderful expression, and then also find an expression for T minus N in terms of the mass, the length of the string, angular velocity. All right, what's happening horizontally? Again, all that's happening horizontally is we're moving in a circle. So I know the resultant force horizontally is mr, and because they're mentioning angular velocity, I'll say omega squared. We have a component of the tension, but now we also have a component of the normal force horizontally as well. The resultant force is acting towards the center of the circle, so the T cos theta will be positive, the N cos alpha will be negative. So there we go. T cos alpha minus N cos alpha will be mr omega squared. Vertically, it's not moving up or down, it's just sitting on the cone, it was saying. So nothing's happening. Vertical forces will equal 0. We have a component of tension going up. We have a component of the normal force going up, but we also have gravity acting down. So T sine alpha plus N sine alpha minus mg is equal to 0. Doesn't actually matter with this when you think about it, which one I made positive, because it equals 0. So I could move them from either side anyway. And I get T sine alpha plus N sine alpha is mg. So what are we trying to find? T plus N. We now have some simultaneous equations. So T sine alpha plus N sine alpha is mg. Oh, in fact, all I have to do, I don't have to use the other equation. I can just factorize the sine alpha and make T plus N the subject, and we've got it straight away. Mg sine alpha. It said also come up with an expression for T minus N. So I guess that's where I'm going to use the other one, because I can do a similar thing. I can factorize the cos alpha, and I get an expression for T minus N. But they said they wanted it in terms of mass, I've got that. Length of string, haven't got that in there yet. And angular velocity. So we need to get the length of the string in there somehow. Okay, so again, have a look at the diagram. Using the triangle in there, I can say radius over the length of the string will be the cosine of alpha. So T minus N then will be, I can rewrite R. R will become L cos alpha. So if I sub L cos alpha in for R, the cos alphas will cancel, and I simply get ML omega squared for T minus N. All right, so they're now saying we're going to increase the angular velocity. So as we know, we saw with our helicopter, that if we increase the velocity, it's going to want to lift. And they're going to do it to a point until n equals 0. As soon as that normal force equals 0, that must be when it's lost contact with the ground, because it no longer has a normal force. Whilst it's in contact with the ground, it has a normal force. As soon as it's 0, it must have lost contact. That's the instant that it's lost contact. So that's what they're saying. We're going to increase it until it loses contact with the cone. So now find an expression for the value of omega in terms of alpha, the length of the string, and gravity. All right, so n is now equal to 0. So I can say tension is mg on sine alpha, and it's also equal to ml omega squared. So I should be able to equate these two to come up with what they want. So if I make them equal, we got to make omega the subject of the formula. So rearranging it, we end up with, eventually, the square root of g on L sine alpha. Okay. Cambridge, questions? And Simon Patel.